Hello, this is Junteng, and the title of our talk is Joint Further Learning and Personalization for On-Device ASR Adaptation. This is joint work with my colleague Ke and others in the speech team. We consider an on-device ASR model, which is a RNN transducer. And this model has the encoder, which is a conformer, and a predictor, which is an RSTM, and a joiner, which is a feed-forward layer plus a softmax. In the remainder of the talk, we'll refer this model as a backbone model. This backbone model is pre-trained on a pen data set, and our goal is to adapt this backbone model to user data. In our experiment, we use the portal production data for demonstration, which consists of 1.2 million utterances collected from 139,000 distinct user devices. In a traditional on-server adaptation setup, this will be a very simple task. First, you would collect the utterances from device to server for human annotation. Then you can use all user data to fine-tune the backbone in a centralized learning fashion. Finally, to further improve the model performance on individual users, after the backbone adaptation is finished, you can insert adapter to the encoder layers and fine-tune on user-specific data. In this work, we consider a slightly different setup, where we want to avoid sending utterances to cloud server for annotation and training. In other words, the data collection and training happens on device. In this setup, the on-server solution is no longer valid and needs to be adjusted. First, human transcription is infeasible on device, so we will need to use machine transcription instead. Second, instead of centralized training, we need to use further learning to collectively train one single model, the backbone model, across many different devices. Finally, to cope with the potential data retention constraints, we propose to jointly fine-tune the backbone with further learning and the adapter with personalization. We'll talk about that in a second. Now, let's dive into the details and start with further learning. As an overview, a further learning system consists of two parts: the client that runs on user devices and the central server that runs on the cloud. On the client side, it downloads the ASR model to serve users and collect user data and perform local model update on device. On the other hand, on the server side, it will aggregate the ASR model trained on the individual devices and generate the next global update, the next version of the global model. More formally, we can write down the pseudocode where the server will send out the model over here, and the device will receive the model and perform the training, and then send the locally trained model to server for aggregation. And then the server will receive the model, perform aggregation, and generate the next version of the global model. Now, in our setup, the federal learning is only used to fine-tune the conformal transducer backbone, and we denote the weight from the backbone as W. On the other hand, the personalized adapter weights we will denote as Q are updated locally on each individual device, but they are never aggregated. Now, both the backbone weight and the adapter weights, they are updated in log steps. In each training iteration, we first train FL of the backbone, and then we perform a personalization of adapters on the same data in the same training cycle. Also, as we discussed, both further learning and personalization use pseudo labels, which are generated by a teacher model on device. And given the drastic different data distribution, we will partition the user into 4 groups, depending on the number of utterances they have, and we'll report the word rate separately for each group. During the pre-training stage, we pre-train the backbone on vendor-collected data. Moreover, we also pre-train the adapter weight to give a good initialization for later personalization. The evaluation of the portrait model is shown in row number 1 and 2 in the table. As you can see that even before adaptation on user data, heavy users with a large number of utterances have a lower word error rate than light users, which can explain why the heavy users use ASR more often. After pre-training, we adapt the portrait model to user utterances using pseudo-labels generated by a much larger teacher model. In this case, we use a 100 million parameter teacher model to train a 11 million parameter backbone and adapters, which have 0.3 million parameters. And we consider 3 adaptation options. The first adaptation option is simply only train the backbone with federated learning. And the second one is to only train the adapters with personalization. And third one is to jointly train the backbone and adapters as we described. As you can see that row number 3 is federated learning results. You can see that FL reduced the whatever rate somewhat evenly for all group users, resulting 8.9 to 12%, 12.9% of whatever reduction relative. And row number 4 is what if you only do personalization. As you can see, that personalization greatly benefits heavy users, as you expect. It achieves 24.6% relative whatever reduction for those users with 50 plus adaptation utterances, but it gives very little benefits for users with less than 5 utterances, which is a vast majority of the users. And finally, by combining federated learning and personalization, we achieve the best of both worlds, giving 8.9 to 27.4% relative whatever reduction across different group of users. In our joint adaptation algorithm, we perform FL and personalization in log steps. A simpler way of combining FL and personalization is to first perform FL to train the backbone until the model converges, and then perform adapter personalization. We refer this method as one-shot personalization, and we evaluated this method, and result is shown in row 7. As you can see, one-shot personalization performs similarly with our joint adaptation method. However, one-shot personalization requires saving the data in a local storage for a long period of time, because it first performs FL, and after FL converges, it performs personalization on the same data. So this may violate some data retention constraint in certain applications. For example, a messaging app that uses voice dictation might delete the utterance shortly after it is transcribed. And in those cases, one-shot personalization is not feasible. In contrast, our joint adaptation algorithm allows continuously learning under tight data retention constraints, which means whenever you have an utterance that is being transcribed, you can simply send it for FL and personalization, for joint FL and personalization, and after that, you are safe to delete the utterance. As you can see from the table, the joint adaptation algorithm actually performs as well as one-shot personalization, despite being more flexible for tight data retention constraints. And finally, we want to show some self-super learning setup. So besides the semi-super learning setup we talked about earlier, where the teacher model is a large 100 million parameter model, in this setup, we consider the teacher model as the model under the adaptation itself. And as you can see over here, although the self-super labels are of lower quality, the joint adaptation method remains the most effective and achieves 6.8 to 17.5% relative whatever reduction across 4 evaluation dataset. That's all for my talk. Thank you very much for your attention.